So, hello everybody. My name is Vojin Zivojnovic, and I'm from the company Agios. And I think that Sushma's previous presentation was really very good, excellent introduction, because I will start exactly at that point. When we started looking at the energy characteristics of devices and tried to experiment at the software and firmware level, we started looking at existing standards which we could use, which describe the hardware from their energy perspective, but that can be used by the software people. So simply, just browsing all EDA, IEEE standards for the word energy. Result, none. Okay, that was a little bit disappointing. So we said, okay, maybe energy doesn't count, but power counts, and of course power counts, and we hit immediately UPF, and we said, voila, this is it, right? We'll take it and we'll write it and make all the operating systems, firmware, and so on rely on that. It was a good start, but not because of the standard. It was because of the people. Because the people involved in that standard have been very, very skilled, very systematic in their thinking. Not exactly what we needed. We needed energy orientation. They had the power orientation, and we didn't want to overcrowd our customers and our partners with HDLs and hardware. We wanted them to continue living their software lives, right? So I started going to the UPF meetings, attending them, meeting people, and so on. And step by step, I became aware that, again, the potential is really in the people, in their knowledge, in their excitement to produce something which is useful to the community, but that we will need to work together. And then came a call, which was a year ago, exactly a year and 2 months ago, of the formation of the low power study group. And by the way, that's an excellent idea. You have a standard, you develop something, you have the second version of UPF, and then you launch an effort to double check, where are we? Have we done a good job? Or are there any other ideas which should be launched? So Yatin Trivedi, he was the right person to lead this exploratory effort. And we started from day one from two directions. One came from the transistor level, and from Liberty, and the other one actually came from the software level. And step by step, now we are a year and a little bit longer after that event, we came to two approved PARs. One is 2415, the other one is 2416. And I will not be talking about these PARs because they're public. You have them on the website. We're inviting people. It's something you can talk to me, to Yatin, to other people who are supporting them. What I want to talk to today is actually a buzzword, and that's the buzzword energy proportional. Because people would expect energy efficient, and people would expect other terms, but I somehow like the buzzword energy proportional because it's different. And you will see why it's different and keeps us thinking all the time. So the energy proportionality as a term was introduced by two of smart Google people in, of course, an IEEE publication in 2007, but in the context of servers. I was not aware of that work until Professor Jan Rabai from Berkeley pointed to, and actually I think 2 years ago he held a talk here at Cadence about low power, and he also mentioned that work, predominantly because it has a concept which I think is very important for that what we are trying to do. In summary, and I would advise everybody to take a look at that paper, in summary I would say it's really about developing machines, and in their context is servers, that consume energy in proportion to the amount of work performed. This proportionality, I think, is important in every device we use and every device we develop. And I will start by explaining some of the key elements of that work, and then drift slowly in something which is not a server, and obviously it's much wider than the just application in servers. So these are two original figures from their work, which basically present the following. The green figure, the green curve shows the power as how it depends on the utilization, meaning how much a typical server, how much power will use when utilization ranges from 0 to 100% of the peak value. Good news is, yes, it's slanted from, when you start with the highest peak performance going down. So it reacts. It reacts on utilization. That's already good news. But the bad news, it stops at 50% of the peak power used by that device. So meaning that even if utilization is 0, you pay the price. Interesting also is that servers do not have this typical bimodal regions of use like in mobile, which is idle and highest power. Their hotspot is mostly in the typical operating region from, say, 20 to 35% of utilization, as you can see here on the lower figure, which basically measured on a class of 5,000 servers, where the utilization was in typical cases. So what they figured out is that the utilization in the standard computing is really around these 27 up to 30%, and that it has only 40% efficiency for this most frequent utilization. Nothing new, but again, very systematic view at what is happening in one particular computing device. What they did next is they looked at how can a device be made more energy proportional. I'm just now like reading the paper for you. No messages hidden or related to that. They simply said what can bring more energy proportional computing, and obviously there have been a couple of ways how you can do that in servers. One is to have components which are more energy proportional. They figured out that CPUs are doing a pretty good job on that side. So that the dynamic range of energy proportionality is 70%. So that you can change 70% up and down for typical server applications of the power consumption of a CPU. Much less for memory and very much less for a switch and other components. The other source where they could gain efficiency was by redistributing activities of the server. So we know about tickless kernels, about time coalescing. Basically, you try to enable the server to sleep as much as possible, meaning that you package or put together all your tasks, launch them, finish the job, and then allow idle modes, sleep modes, and similar suspend modes to kick in. And then, of course, the third one was how to properly provision the server farms, how to organize them in terms of certain other servers taking tasks of a, say, cluster of servers which could be put in sleep. They figured out that with such attempts and such steps, they could reach much higher efficiency, and the power efficiency was going up to 80% for the most frequent utilization. Now, servers is one example, and the other examples, I will be just browsing through a couple of them. This struck me really strong. This was a measurement by a telecom provider who was part of the initiative by the European Union to see the ways how telecommunication equipment could be put in a say lower energy limits, and this equipment is installed heavily, of course, in all the countries in the world as well as in Europe. So this particular router was experiencing during the day, 24 hours, a traffic variation of 308%. At the same time, the total power consumption variation was only 0.4%. So no, it doesn't. I mean, whether it works or not, whether it is traffic or not, it's really consuming the same power. And also in the Google paper, they also mentioned switches, routers as really big culprits of energy consumption. This is similar, but you will see why it's not the same, obviously, because we are not analyzing the mode of the same device. We are here analyzing the simple application of video streaming. If you stream a full 1080 HD video on Apple TV, you will consume 2 watts. If you do the same on a gaming console, not to be named here, you will consume 73 watts. And this is from the Natural Resources Defense Council report. Interesting enough, 80% of the time the game console is used for Netflix watching, according to their statistics. So obviously we have here certain disproportionality. Obviously this gaming console device was not built for this application, which probably was not intended at the moment when it was designed and it was produced. The third domain of energy analysis is what is now very actual, are the IoT devices. Here's an example of a IoT microcontroller. You will see a lot of states with very detailed information about the currents as well as the wake-up times. Observe, please, microamps and microseconds. So all of them count enormously on devices which, as Dennis said, should last for years on, say, AA or triple or small button cell battery. So these examples just emphasize what Sushma, I think, said, and these are the use cases. So whereas 1801 needs these use cases to prove its validity, to make it work, and to basically detect any issues with the standard or maybe in the design itself, when you bring energy into the equation, they're crucial. Depends what are you doing at that moment. So what is the purpose of that device? The purpose of the power management you have at that moment? What is the way that device will be used? And then what are you paying in energy? So based on these examples, what I wanted to just send as a message is really we need to keep this consumption of energy in the device proportional to the work we are getting from that device. So this here is obviously non-proportional. Here we have a certain proportion. On the right side, we are literally wasting hours and hours, and these video streamings are not like a couple of seconds and that's it, or like a short game. These are long periods of time. The previous version of the same device was running at around 200 watts. That was the version 2 years ago. So keeping always in mind the amount of work we get delivered and the amount of energy we spend on that work, I think this is the key question for all of us. Now the question is how to put that now in a standard, how put that in a form which we can start communicating about that. So I will go a little bit further and simply say what we will need to do, we need to start learning from nature. And that's obviously here shown with this cheetah. We still think all the time like we are running for maximum performance. But nature design its things, its products, including us, for maximum efficiency. And the most frequent state of this cheetah is really sleeping or just waiting to start running to catch the prey. The energy management we have today, and you can see it here on this dotted curve, this is the standard management. Basically here, you see the opportunities for, this is the work to be done, the blue one. So this dotted line is not proportional because first it didn't catch this opportunity to sleep, and then it started catching this opportunity but with a certain delay. The red curve is really the energy proportional management. So it catches all the events, it's really fully proportional, establishes the proportion between the work which needs to be delivered, as well as the consumption of energy consumption in the devices. How can that be achieved? It can be achieved by taking the device and grabbing all the relevant information around that device, system state, meaning the current status of all the LDOs, all the blocks in the system, all voltage rails, all clocks, and so on. Feed that back into an observer. Similarly, we need to observe what's going on in the software. We need to say, video started. But when the video starts, it probably is processed in a pipeline. So are all three elements in the pipeline of equal duration? Probably not. Probably is one block going to be dominant. So why not to sleep the other blocks which are just waiting for something to be processed? But then somebody will say, can we put that in a sleep state fast enough? So this here is one hypothetical management system which in essence has the device model, which is here, which is fed with the system state, all the hardware observation, all the software observation, plus all the impact observation. A good example of an impact observation would be a block which is GPS. It suddenly switches to more satellites or has tougher time computing coordinates. This impact is not directly visible through software, but it will impact the state of the complete system. Once we have this device model, we will be able to compute the almost optimal controller for controlling the device. In this sense, that could mean the task has observed that a certain video has started. It determines the device model and sets the controller, say, to the maximum frequency for the CPU, to a certain setting for the memory block, or for a certain exclusion of, say, certain peripherals which may not be needed at that time. This is an example of such a sequence with here are 6 rails, and how this is reflected in the no energy proportional management and total with energy proportional management here in red. And this is an example of a start of an EPM, which immediately calms down certain components. After a while starts an FTP, it ramps up the process. When the end process is detected, it goes back to the previous EPM level, and then at a certain moment it goes into the emergency mode or gets into deeper sleep mode. Now, this information about the rails is included in 1801. What is not included in 81 is if we want to do something similar with a clock gate tick, because clocks are very important. It also very much changed the energy profile of a certain component. What also is not included, and which is the biggest problem for us, was how should we deal with time? Because power is one thing, energy is something else. We need to be able to compute the amount of power times time to get to the energy consumption in that particular case. So we ask ourselves even a step further, saying how should these people who are in the development chain interoperate when it comes to energy? So on the left side you see the IP people who produce these great IP components we spoke about here. Semiconductor company brings them together in an SoC. Don't forget the motherboard. The motherboard, not only SoC is the consumer of the energy, it's the whole motherboard. And then on top of that, you also have the applications which run certain software. So in this chain, we have done great job in the functional interoperability, meaning these guys here have C, C++ or Java, here board tools from great EDA companies. We just spoke a lot about SoCs, and the whole IP field is delivering great components to be put together. So we have system C, IP exact. We have VHDL Verilog. We have different verification procedures. But what about energy? I mean, in power, yes, UPF is doing a good job. But what counts at the end of the day is really the energy of the complete device, together with the software in the real environment, which is a phone which cannot run more than 1 day of use, although we would like to have at least a couple of days of use, and some of us would like to have them as a calculator, a couple of months of use without recharge. So we believe that at this moment there is a suboptimal energy interoperability between all these participants, that they communicate with very informal, misleading information very often. Data sheets, Excel data sheets is the favorite way for them to communicate. Maybe in this space, UPF and similar have a good ground. Nobody here knows what UPF is, although they're very interested to have the lowest energy, best energy profile. So in order to address this issue, we started with some analysis of what is in the essence of that what we need. And this is just one slide on some of the proposals we have been making and discussing in the low power study group about operating modes, operating states, operating points. However, all of that needs to be matched to the software, meaning that an operating mode by itself does not present enough information for energy consumption if it's not related to a certain event from the application, so that we can calculate the total energy consumption of that for that device. Yes, 1801 system level group has started looking at extending the elements of 1801 power states, what Sushma has just shown, but we believe we will need more than this. And this actually generated this new IEEE PAR 2415 to look at energy proportionality. And the key is the tight interplay between energy-oriented hardware, so not just power, but energy-oriented hardware, and energy-aware software. The software needs to be aware of the fact that it is causing energy to be spent, and primarily because certain pieces of software may be executed in a different way to be for more energy-saving results. This activity also requires pretty much very new design verification, modeling, management, and testing abstractions. So we are looking into that. As we said, we are working very closely with UPF 1801 to add on top of the voltage distribution, clock trees, reset trees, scenarios, and similar. And the key guidance is really for us to go top down, to start with the software and go down into the hardware to be good, excellent friends with the software people and have a good partnership with the hardware people. And that's obviously not easy to achieve because we have the design automation hat, we have the hat of the typical hardware people, but again, as I started my talk, I believe the people who we worked with have enough wisdom, experience to learn the software language fast, the way how the software people communicate, and use the systematic way how EDA is solving problems to become attractive to the Linux people, to the Windows people, to the firmware designers, and so on. And just to finish, while discussing in the low power study group, he said how we should position that, and then John Biggs from ARM came with this, what I'm now calling Biggs analogy, really representing a cave. I mean, we didn't feel like in a cave in a low-power study group. I mean, Yatin, right? But we felt challenged to understand what are we doing here. And he said that basically the stalagmites which grow, you know, which are have a firm foundation in hardware and basically grow up. This is the UPF 1801. And that effectively we are with P2415 starting the stalactites, which grow down, which, you know, drop by drop and actually contribute. That's a nice analogy. Contribute to the stalagmites, because without those guys, these guys would not be there, right? And what we also figured out that one day, hopefully soon, we will need to connect those. And we, in K terminology, this is columns. And basically, this is the power management description. A formal way how to describe the power management will need to be added to get to our ultimate goal, and this is to form the column. So please join us for this effort, which was approved by IEEE in the August 21st, 22nd meeting. We had a press release on the 16th of September, and the effort is ongoing. We are now asking for contributions and people who are willing to participate. Further information you can get from me. Other people involved with them are Yatin Trivedi, or pretty much everybody who deals with power in the IEEE side is, I'm sure, informed about that project. Thank you very much.